Hello, my name is Elijah Spears.
And my name is Dan Kelly.
We're seniors in the MSc program at Boise State University. We also work in the Nanoscale Materials and Device Group, where we primarily study DNA nanotechnology and its applications. We're going to give a video presentation for our MSc 310 class, Electrical Properties of Materials. We'll discuss Fick's first law, which is the relationship between net particle flux and the driving force, which is concentration gradient. To start off, we'll introduce the idea of particle flux. It's known that by virtue of random motion, gas particles diffuse from high concentration regions to low concentration regions. An example of this is a hot pizza in a room. When the box is opened, the gas particles, what you smell, will move or diffuse from high concentration in the closed box to a lower concentration, being the rest of the room. And depending on the temperature and size of the room, and after some duration of time, all the gas particles will be distributed more or less evenly throughout the entire room. This is by virtue of the second law of thermo. To demonstrate this, we've recorded a short experiment. Using the same volume of water, two different dye concentrations were dispersed onto the surface of the water. Based on the concept of the concentration gradient, we expect there to be a higher driving force for diffusion in the beaker with the 1x dye. With a higher driving force, the same volume of dye should take less time to diffuse and mix into the surrounding solution. We can see from this experiment that the higher concentration mixes into solution after about 40 seconds. It takes over a minute for the diluted dye to fully mix into solution because there is less of a concentration gradient or driving force. It should be noted that fluid dynamics do play a role in this experiment. However, since the beakers of water were handled in more or less the same way, we can ignore this effect for the purpose of this demonstration. Now that we've got a general idea of what diffusion is, we can formally define particle flux. If we recall that whenever there is a difference in concentration, there is a net diffusion, or flux of particles in the direction of decreasing concentration, just like the dye mixing into solution. We can quantify the particle flux, gamma, just like current, as the number of particles, but not charges, crossing a unit area per unit time. So, if some number of particles cross an area in some amount of time, then by definition, the particle flux is this equation here. Now, if these particles are charged with some charge Q, we can define the electric current density J, which essentially is a charge flux and is related to the particle flux by this equation. Let's now apply this concept to a semiconductor material. Suppose an electron concentration at some time t decreases in the x direction. To simplify this concept into a one-dimensional problem, we'll consider the electron concentration to be decreasing only in the positive x direction. We know that in the absence of an electric field, the motion is random and involves scattering from lattice vibrations and impurities in the material, just as we saw the dye diffusing throughout the fluid. Now, we can take L as the mean free path in the x direction, and tau is the mean free time between collisions. The electron moves a mean distance L in the positive or negative x direction. If we evaluate the flow of electrons in the positive or negative x direction through the plane at x naught, we can determine the net flow of electrons in the positive x direction. In order to derive Fick's first law, we need to look at the expanded view of the region at x naught. Half of the electrons in x naught minus L will move towards x naught and the other half away from x naught, and in time tau, half of them will reach x naught, as shown in the figure. If N1 is the concentration of electrons at x naught minus 1/2 L, then the number of electrons moving toward the right to cross x naught is 1/2 times N1 times A, the area, times L, the mean free path. Thus, A times L is the volume of the segment. Similarly, half of the electrons in x naught plus L will be moving toward the left and in time tau will reach x naught. Their number is 1/2 times N2 times A times L, where N2 is the concentration at x naught plus 1/2 times L. The net number of electrons crossing x naught per unit area in the positive x direction is the electron flux, gamma sub E. Factoring gives gamma sub E equal to negative L over 2 tau times N2 minus N1. Because the mean free path is small, we can calculate the quantity N2 minus N1 from the concentration gradient using this equation, where N2 minus N1 is approximate to dN over dx times delta x, which is equal to dN dx times L. What this says is that the change in concentration with respect to x times the change in x is equal to the change in concentration with respect to x times the mean free path. Now we can write flux in terms of the concentration gradient as gamma sub E equal to negative L squared divided by 2 tau times dN dx. We can now arrive at Fick's first law, which states that the net electron flux, gamma sub E, at a position x is proportional to the concentration gradient and the diffusion coefficient d sub E, where the constant d sub E is equal to L squared over 2 tau.
Since the concentration gradient is the driving force for flux, the characteristics of the curve, which was previously introduced and is this one here on this slide, has a few implications. The first implication is the direction of the curve. This means the flux is occurring towards the right of the membrane, which happens to be when the higher concentration is on the left and lower concentration on the right. This gives a positive flux in the positive x direction. Conversely, if the slope was drawn to be positive, this means the concentration is higher on the right-hand side of the membrane and lower on the left-hand side, giving a negative flux occurring in the negative x direction. One other noticeable characteristic is the value of the slope, or how steep the curve is. When the curve is steeper, the flux is greater, and when the curve is more gradual, the flux will be lower. This effect of larger flux was demonstrated in our opening video with the higher concentration of dye being dispensed into the water. We can relate flux to diffusion of electron and hole pairs, but first we need to know what electron and hole pairs are. In a semiconductor, electron and hole pairs, a hole which is just the absence of an electron, are generated when an electron jumps from the valence band to the conduction band due to some incident energy source, leaving behind a hole in an atom. Holes have a positive charge and electrons a negative charge, as we know. Now, imagine we have a semiconductor between two electrodes. one of which is semi-transparent. Now, an external electric field is applied in the positive x direction. At the same time, light is shown upon the semi-transparent electrode. The light will create an excess of electron and hole pairs, giving rise to a concentration gradient in electron and hole pairs at the surface. Now, under the application of the electric field, which is the driving force here, the electrons diffuse to the right and drift to the left, where there's a lower concentration of electrons. And the hole pairs diffuse and drift to the right, where there's a lower concentration of holes. Since we now have drift and diffusion of the electrons and holes, it is noted that we must add a drift component when relating Fick's flux equation to current density. For electrons, Fick's law as related to current density becomes J sub E, which equals the electron charge, E, times the number of electrons, N, times the electron drift, mu sub E, times the electric field, E sub x, plus the electron charge, times the diffusion coefficient of E, d sub E, times the concentration gradient of electrons, dN over dx. Very briefly, drift, in this case, is just the velocity at which electrons or holes move through a material under an applied field. Now, for holes, this equation becomes the current density of holes, J sub H, is equal to the number of holes times the charge, E times P, times mu sub H, the hole drift, times the electric field, E sub x, minus the electron charge, E, times the diffusion coefficient of holes, d sub H, times the concentration gradient of holes, dP over dx. The only difference here is the negative sign, since the diffusion is occurring to the left, negative x direction, and the p, since we are accounting for the number of holes rather than electrons. To help convey this concept of an electric field being the driving force, we will use a method of DNA purification, which also relates to our research that we conduct. Polyacrylamide gel electrophoresis, or PAGE, is a method where DNA is purified by means of an applied electric field. The DNA is pipetted into a polymer material that contains small wells. Electrolytic buffer solution is in contact with the top and bottom of the gel. A thin platinum wire is present in the apparatus to provide an electric field in the solution from top to bottom. Once the driving force of electricity is turned on in the apparatus, the negatively charged DNA is attracted towards the positively charged electrode, similar to the electron hole semiconductor example. In this video, the red bands, which is a dye attached to the DNA, is seen to move vertically through the gel. The blue dye is just an indicator to show when the purification has reached completion. When the blue dye is near the bottom, the necessary diffusion has been achieved. This video was a 2-hour time-lapse condensed into 29 seconds. So that's it. You hopefully now have an understanding of Fick's first law as it relates to concentration gradient and diffusion to flux. We hope you enjoyed our video.